Hey there, in this video I want to talk about the Fourier series. So in some ways the Fourier series is analogous to a Taylor expansion. It's a way to write a function in a different form. Specifically, this needs to be for a periodic function. And let's say our periodic function has some range negative L to L. And it's pretty trivial to shift your range. So if your range was 0 to 2L versus negative L to L, that's not really a big deal here. And so periodic meaning that our function repeats. So, if we made some kind of graph over negative L to L, if our function looks like this, then it repeats afterwards. And I chose kind of a weird shape, so it's actually going to have a bit of a discontinuity, but hey, that's okay. In any case, if our function has that form, then we can always write it as a summation made out of simpler parts, specifically made out of sines and cosines, or equivalently made out of complex exponentials. And the nice thing about a complex exponential is it contains both a real cosine and an imaginary sine component, so it does the whole thing all at once. And Python is able to use complex numbers no problem, so this is actually the preferable way for us to do it. We're going to do a summation here. And k is going to be an integer counter. We're going to start at negative infinity to positive infinity. And if we actually had infinite range here, then we would have an exact representation of our function. Typically, we truncate our range to some finite values that's close enough. And then in here, we're going to have a coefficient times a complex exponential. We'll do I k pi x on L. And that pi x on L business, that's taking care of the having the right sort of range. So that's consistent with being from negative L to positive L. And now the coefficients in here are given by their own sort of integral relationship. So each gamma sub k is a 1 on 2L, integrate negative L to L, and that term out front is like a normalization factor. We take the original function f of x and we multiply it by a complex exponential, this one with a negative I in it, but otherwise being the same. And I guess we could put a box around that. It's kind of a big box, but that's our Fourier series. Now, if you're wondering, why does this work out? It has to do with the properties of integrating complex exponentials over a complete period. So if we look down here at this line, we have f of x, which we are saying up here is made out of a bunch of complex exponentials of different powers, times another complex exponential. And so what can happen is when we multiply an exponential with a different exponential, and these might have different values. In general here, f of x has all the different k values in it. And this is just for a single k value. So as we multiply these, typically when you multiply these two exponentials, you're going to have some kind of subtraction here, and you're going to have an argument left over that looks like this. So it's going to be a plus or minus I to some number, I x on L. And if we integrate that, let's look at what happens. It's a lot like integrating a sine or a cosine over a complete period, and if you do that, you're left over with nothing. Positive parts cancel out the negative parts. And this is true as long as n is not 0. But if n is 0, so that would be matching up the k's. So if we match up our k's and n is 0, then we're going to have exponential 0, which is just 1. And integral 1 dx is just going to be the two limits subtracting each other, so it's going to be 2L. So in other words, this works down here. This line works because only when we pick out the term of f of x that has the same kind of coefficient will this integration survive. Otherwise, it always gives us 0. This isn't really a great proof, but it's more of a justification for why it works. You can look up in a math methods book exactly where all this comes from. Let's try an example problem. We're going to do a square wave, and we're going to do it by hand, or at least we're going to do some of it by hand. It turns out it gets pretty tedious calculating all these coefficients by hand, but hey, we have a computer. We can program it to calculate as many coefficients as we want. So my f of x here is going to be equal to 1 or negative 1, repeating over and over again. It'll be equal to 1 in the range negative 1 to 0, and equal to negative 1 in the range 0 to 1. So let's make a quick graph of this. Okay, so we are positive here, negative here, and then it's going to repeat. And what we sort of care about is just this region right here. ranging from -1 to 1. Okay, and what we're going to do is we're going to calculate just a few of the coefficients. So we're going to start with gamma 0, do gamma 1, and we'll do gamma -1. And what I'm looking for here is there any sort of symmetry, specifically between gamma 1 and gamma -1? And gamma 0 kind of seems like a special one, you know, because it's like right in the middle of the range. So let's start with gamma 0. So to find gamma 0, I'm going to take 1 on 2L, and L was 1 in this case, so that's going to be 1 on 2. Integrate -1 to 1. F of x times e to the 0 dx. This is me plugging in 0 into that exponential. And then the f of x is going to break into two pieces because we have the top part and the bottom part of the domain there. So we're going to integrate -1 to 0 plus 1 dx. And then we're going to have -1, so I'll put the minus out front. Integrate 0 to 1 dx. And this is going to give me 1/2 minus 1/2, which is 0. Okay, so the gamma 0 term is 0. And actually what this term ends up representing is the average value of the function. And in this case, the average value of our function is 0. Half the time it's positive, half the time it's negative. So that makes sense. Now let's look at the gamma 1 term. So the gamma 1 term, once again, 1 on 2L will just be 1 on 2. Integrate -1 to 1. F of x e to the negative pi x. Now we're plugging in a equals +1 and L still equals 1. dx. Okay, so if we split this into its two pieces, I'm going to have a 1/2 e to the negative I pi x, and then integrating that pulls down a negative I pi, and then the limits are -1 to 0. We have a minus sign for the second part because f of x is negative there. I'm going to have a 1/2 e to the negative I pi x on negative I pi, integrate 0 to 1, and then we do some algebra, and we're going to find that this one doesn't completely cancel out. Instead, I'm left with a -2 on pi times I. All right, and let's see if we can fit the other one over here on the right. Let's do gamma -1, which, as you might guess, should be pretty similar looking. It's going to have a lot of the same terms. The only difference here is in the exponential, instead of being a negative here, it's going to be a positive. So we're going to have a positive I pi x dx. Okay, we plug that in and we crunch through the algebra. That's really the calculus. And then the algebra. And when we're done, we're going to get a positive 2 on pi I. Oh wait, maybe I have these backwards. Let me check my work here. Yeah, sorry. Little typo here. This one is the -1, and the other one is the +1. And I know that actually they have to match each other because gamma -1 has to be equal to the complex conjugate of gamma 1. So these things are symmetric in the sense that they're complex conjugates of one another. And the reason for that ultimately is because the original function f of x was real. If f of x was a complex function, then we don't have this symmetry. But when it is a real function, then we do have this nice symmetry. And you could sort of say, well, it's kind of like half our coefficients are redundant. In other words, we already know what they're going to be because they're going to be complex conjugates of one another. Okay, so now let's jump over into a notebook and see if we can make Python calculate some other coefficients for us and do it faster. So here we are over in the notebook, and I want to play around with our square wave. I think first thing we should do is plot it just so we can remember what it looks like. So I want to make some kind of function that keeps repeating itself. And so a good way to get a function that repeats itself is to use a modulo. So that would be something like x modulo 2 would keep repeating itself. Although I don't really want quite x modulo 2, that's going to look kind of like a triangle or a sawtooth wave. It's going to have a slope to it. So what I want to do is basically take the sign, the SIGN sign of this thing. Okay, now that would be good, except it's not going to be centered quite right. What I want to do to get it centered the way I wrote it in the previous video is to subtract 1. And so I think this will be what we want to see. We'll plot it to make sure. So let's give it a bunch of x values here. We're going to go from -2.5 to 2.5. So this should give us, several repetitions because the range is -1 to 1. Let's do 100 steps, which is, for something this this flat. That's kind of excessive, but hey, who cares? Computer can do it for us anyway. And we're going to do a plot here of x and f of x. I guess blue's fine. Let's plot the we'll plot the x-axis as an xh line, and I want to set the color here to black. Okay, let's see if that looks like what I'm expecting. Okay, definitely a square wave. It's positive from -1 to 1, negative from 0 to 1. All right, great. So that's just what we had in the when we were working by hand. So now what I want to do is I want to calculate a bunch of those coefficients gamma. We're going to make a function that does this for us, and then we can just call it repeatedly. So it's going to be a function of k here. Then to calculate gamma, we had to do an integration. So we can do quad to do the integral for us, and then it can return that. And then so to do an integration, we have to have some kind of integrand. So we can put that as an inner function here. It's a function of x, and what we're going to have in this case is 1 on 2l, or 1 on 2, since l is 1. We want to multiply that by f of x, which I defined above. We want to multiply that by the complex exponential. We can make a complex here. We just have to put a complex number. Remember, Python uses j for its complex numbers. The -1j is the same thing as -I times k times np.pi times x. Okay, so good, and now we should be able to do quad. Now we have to be a little bit careful here because this is a complex function. When we feed it to quad, we're going to get kind of a surprising result. We are going to discover that quad ignores the imaginary part. It only works with the real part, and that of course is throwing away a good portion of our answer. In fact, the example coefficients we did were all imaginary, so it'll throw away our entire answer. So what I'm going to do here is use the idea that a complex number is equal to real plus imaginary. So my return values here are going to be I real plus I, so in this case 1j, times the imaginary part. And I'm going to basically just integrate twice. I'm going to integrate the real values of the stuff here, and then I'm going to integrate the imaginary values. So we can get I real from quad. And I think I already have integrate imported. But we'll be watching for that error message just in case. And so what's going to go in here is, I mean, normally I would just type integrand here, but I want just the real part of it. So I'll do np.real of the integrand. Then we could do the same thing for the imaginary part. We have to give this limits, and those would be -1 to 1. Okay. So now we can copy this and get the imaginary part. One more thing, the return value of quad is the integral and an error estimate, and I don't care about the error estimate. I don't intend to return it, so I'm going to use an underscore here for don't care sort of variable. And let's see, as far as I know, this should work. So let's try it out. Let's print some of our coefficients. So we'll do for k in range, let's go from like -5 to +5. So -5 to +5 plus 1 is 6. And then let's print something all pretty like. So we'll print, say, k equals the current value of k, and we'll do 2 decimal places there. Put a colon, and then we'll do, say, gamma of k, each part printed with 3 decimal places. So this will work with complex numbers just as well with floats. It'll just do 3 decimal places for the real and imaginary part. Okay, let's just see if this runs. No, something's mad. Doesn't like what? Float argument must be a number, not a function. Okay, what silly thing did I do? Oh, it's right up here. I gave it integrand instead of integrand of x. Okay. Right. And that's because this is a lambda function, lambda of x, so it needs to pass in some kind of x, which would here be this argument. So there we go. Here's our coefficients, and in particular, I want to check right here. Do these match what we got when we did it by hand? So we got 0. The k equals 0 was 0, and it looks good. When k was +1, we had. Let me just look it up here. We had a +2 on pi times I, so 2 on pi would be around 0.6. All right, and then for our -1, hey, looks good. And so you'll notice, in fact, that the pattern here of the complex conjugates for the positive and negative values, that holds here. So like for k equals 3, we have 0.212 versus negative 0.212. You also notice that in this case, we don't have any even coefficients whatsoever. And that has to do with whether the function is even or odd. This particular function is a purely odd function. So as it happens, it will only have odd coefficients. If this was an even function, it would only have even coefficients. And if it was like a mix, if it wasn't even or odd, then we'd have both coefficients. Okay, so now let's look at trying to reproduce our function here with a Fourier series. But we're not going to do all infinite terms. We're going to do less than infinite terms. So we can use a lot of the code we already wrote here. I might need to throw a vectorize in front of this thing. We'll see. But basic idea here is what I'm picturing is I'm going to import some widgets, and then I want to make a slider, a range slider that will represent the range of values that we'll use for gamma sub k, so basically the k values. So if I did like k -5 to 5, that would be kind of like this here, and then it would plot on top of that all those complex exponentials for us. So let's get our widgets imported. IPy-widgets as widgets. From Python, we're going to import display. Okay, and I guess that can be its own cell. And then let me just think about where we're going here. So when we're done with everything, I'm going to have something like slider equals widgets dot something like int range slider, I think it's called. Tab completion doesn't want it. There we go. There we go. Int range slider. That sounds pretty promising, right? Let's see. Slider that represents a pair of ints, min to max. That sounds perfect. We'll do an int range slider. We'll set the min to -10. We'll set the max to +10. And we'd better turn off continuous update. This might be kind of slow. Okay, and then we can build our widgets, which I'll call GUI, and then that'll be an interactive. That interactive needs to call some kind of function and its argument. So let's call our function visualize for lack of a better name. We'll have to write this function, and we're going to give it a range of k values. So let's call it k range, and we'll set that equal to our slider. And then we will display it. Okay, so we need to define here our visualize function. Takes k range as its argument. And so its job is going to be to make a graph for us. So this is mostly plotting code. So let's extract k-min and k-max from k-range. The way these range sliders work is they return a tuple, the min and the max. So we're going to pull those out here. And so then we'll use those in our graph, and then we're going to do an x, bunch of x values. We'll get those from a linspace. Like we did before, we'll go -2.5 to +2.5 in 100 steps. And then we're going to plot. This is our original function. So this is the same f of x that I had way back here at the beginning. I haven't changed it yet. So this is just going to redraw the actual square wave for comparison. Let's make it a black color so it really stands out. And then what I want to plot is the Fourier series. Now the Fourier series can have real and imaginary components, so I better make two plots here. I want to plot the real part and the imaginary part. And now that I think of it, I need some kind of function to be plotted, so I think I should make a new function called f_approximate. And f_approximate is going to be a function of x, k-min, and k-max. Let me just make this a lowercase a. Okay. And the idea here is what this function is going to do is it's going to plot a bunch of complex exponentials in the range k-min to k-max. So basically, it's going to be a subset of the full infinite Fourier series. And so there's going to be a bunch of k values. We can get those with, say, an a range. That ranges from k-min to k-max. I guess we really want k-max plus 1. And by default, this will be step size of 1, which is good because these need to be integers. And then we are going to return a sum of a sum that basically looks like the Fourier series. So in here, there's going to be gamma k, and gamma k will be multiplied by a bunch of exponentials, complex exponentials. So we're going to have a 1j in here times k times np dot pi times x. Okay, so as long as there's no typos in here, then this should represent some of the Fourier series. And if in principle we put infinite in here, I mean, Python would be mad, but in principle, if these were infinite or really, really large, this should end up looking exactly like the original function. Okay, now let's see. I'm almost certainly going to need to vectorize some of this stuff. Yeah, I definitely want to vectorize this one. I have to remember how to spell. Okay, so we're going to vectorize this one. And if this is vectorized and it's calling gamma, gamma better be vectorized. Otherwise, we're going to see all those error messages about a.any and a.all that we don't want. All right, so now this thing is vectorized. We can now plot it. So we can plot x and the real part of f approx. And we want to give it x, k-min, and k-max. Better give it a label just so I can tell which is which, and then we'll put a legend in here. So we'll call this real. We're going to do the exact same thing, so I'll just copy and paste this code, but with the imaginary instead. Let's plot the imaginary component. Now, we really shouldn't have any imaginary component because we started with a real function, but, you know, let's just see what pops out anyway, just to see what happens. Because mathematically, there could be an imaginary part. Show the legend, and we'll show the whole thing. And if it's been a miracle and I haven't made any typos, in principle, this should give us a cool little widget. Let's see what happens. I got a widget, but I also have an error. Not too unexpected. Let's see, what's wrong? Only size 1 arrays can be converted to Python scalars. Now, I noticed it plotted this part. So it must be mad about the fapprox stuff. Oh, okay, I figured it out. I forgot my @ here in front of the vectorize. So I was just naming the function without actually making it a function decorator. Oh, what a silly error. All right, so if we run that and run that. All right, parentheses in the wrong place. So I thought label was inside real and imaginary. Start crashing. Hey, there we go. All right. So finally something for us to play around with. So if we just use k -5 to 5, we can see we get an approximation. The imaginary part does end up being 0, and the real part is, it's kind of like the square wave. And if we boost these to -10 to 10, we should get a better approximation. Give it a moment. That might actually just be the -10 to 5. Give this another moment to do the second part of the update. There we go. So we've got the imaginary part still 0, and then we've got a better approximation. What you notice there is if we are unbalanced, we end up picking up some imaginary component. So you always want your range here to be symmetric, about 0. And then we can see, like if we did a real small range, like -1 to 1, we're going to get a pretty poor approximation to the original function because we don't have so many terms. All right, so it gives us sort of something to play around with, gives you something to play around with to get sort of a feel for like what the different terms in the series actually represent. I mean, we could do something really crazy, like just do, only some positive coefficients, which should be an absolutely terrible fit to the function. Yeah, so like that's not very great.